Welcome to mini lesson 18. Today we start discussing the statistical mechanics of the ideal gas. Excuse me. Up to now, what we've been doing is dealing with the ideal gas in a couple of ways. First, we talked about it empirically via the empirically determined equation of state, the ideal gas law. Then we did what's called kinetic theory, which is sort of a cobbled together specific version of statistical mechanics that we apply only really to the ideal gas. And then in addition, we went a little bit beyond that and discussed implications for thermodynamics. And so what we're doing now is kind of doubling back. And instead of doing the kinetic theory, which is not a general theory, it's sort of a specific approach. And we're doubling back and we're going to replace a kinetic theory with statistical mechanics, right? We think we have a general theory of statistical mechanics, beginning with the fundamental assumption, using Boltzmann's entropy, and focusing in on multiplicity. So these next 4 lessons are fairly difficult, and you should expect to struggle with these lessons. I'm trying to slow walk it a little bit so that everybody has a chance to stay on board, ask questions, pay attention to the textbook, things like that, because it is something that's, it's going to take some time to get used to what we're saying here. So we're in section 2.5 of Crane. So let's start out by discussing what we mean by the microstate of a classical ideal gas. So if we need to specify the state of a bunch of classical particles in this gas, all we really need to do is give their positions and momenta. And that at any instant will tell us the state of the gas. So if we had this gas of 4 atoms, we give x1, y1, z1, px1, py1, pz1, right? Where the first 3 are the positions of this gas atom. It's considered a point particle. And the next 3 are the components of the momenta of this gas atom. And likewise for all the other gas atoms. And so to specify the microstate of the whole gas, we would give a list of these ordered 6 tuples. Right? And so in general, if you had an n particle system, you would need to give a list of these 6n numbers. Right? So each microstate has 6n numbers. And when n is 10 to the 23rd, that's obviously an impractically huge set of numbers to write out. But it goes even deeper than that, the sort of problem that we're dealing with, and that is we need to count these microstates, right? How many microstates are there? I'll say more about that in a second. But both X and P, certainly in a classical picture, can take on a continuous range of values, right? And so we can't just use sort of discrete combinatorics to count discrete members of a set like we did for the 2-state paramagnet and the Einstein solid, right? In those cases, the microstates were sort of being specified by a discrete number of units, a discrete set of possibilities, and you could use these discrete counting tools. It's not the case here, so we're going to have to develop new tools, and that's what the next 4 lectures are doing. And this lecture is kind of a gentle introduction to it. But before we go on, we can't just say we want to count microstates. That's actually not valid as a physics idea. What you need to do is count microstates that are consistent with the given macrostate. So we do need to first say, what is the macrostate? And then we say, okay, how many microstates are consistent with the given macrostate? So the macrostate of the ideal monatomic gas will be specified by telling how many atoms are in the gas, what's the volume of the gas, right? What's the total space taken up? And so in this case, it's important to note that the volume of the gas, the macroscopic parameter, is connected to the microscopic positions of each atom. right? Sort of the range of values that the positions can take determines the volume of the gas. Or vice versa, the volume of the gas determines the range of values the positions could take. Okay? And then the internal energy U, the total energy of all the atoms in the gas, is the third macroscopic characteristic, macrostate specification, right? So we know about the internal, so N and V in some ways I think are regarded as sort of obvious parameters. But we actually know a lot about the internal energy U, and in particular, the fact that we're dealing with an ideal gas tells us that the atoms have only kinetic energy, right? And so U is equal to the sum of all the kinetic energies of all the atoms in the gas. So kinetic energy is P squared over 2m, where the P squared here has to include all the components, but I'm not going to write that out explicitly because it gets too cumbersome, right? But for each I, there's a P squared value that's Px squared I plus Py squared I plus Pz squared I. All right. It's actually important to be okay with this idea that the meaning of ideal gas is that you only have kinetic energy. If there were a potential energy factor involved in this discussion, the gas would no longer be ideal because you would essentially be saying there are interactions between the gas atoms. So this is really important to have this macrostate specification in mind because that tells you how you're supposed to do the counting of the microstates, right? You don't just want any old microstates. You want ones that are consistent with a given NVU. So let's start with an example. We're going to do two examples today. And again, they're just meant to kind of slowly introduce the perspective that we take on this. And I think it's an important perspective going forward for a physics major. And then I guess if you're not a physics major, maybe it's worth knowing how the physicists think about the stat mech of an ideal gas. Maybe that's why you took this course. I don't know. So here's our idea. We're going to think about an ideal monatomic gas with only one atom moving on a 1D line. All right? So there's basically a gas atom confined to move in only one dimension. You might think that that's sort of ridiculous, that it requires some potential to confine it, and that's probably true, but you know, you can sort of zero that out. It doesn't really matter if it's just a fixed confining potential. Just call it zero, and then it's an ideal gas. So an example of this in a real physical situation is a gas atom adsorbed on top of, say, a carbon nanotube, which is a one-dimensional object. You're then constrained to move only along the nanotube, and you can be treated as a 1D ideal gas. So it's not the thing that's artificial about this model is thinking about only one atom. It's not artificial to think about one dimension. So here are our macrostate parameters. U is the kinetic energy of the atom, so P sub x squared over 2m, where m is the mass of the atom. The number of atoms is just one, fine. And then we don't have a volume here, but we do have a region of space where the coordinates of the atom are allowed to be, and that's anywhere along this line of length L. So we're just going to call L our volume, okay? So the possible microstates of this system are the ordered pair x and p sub x, right? Subject to the macrostate constraints. And the macrostate constraints are, so I'm going to actually x out of here and write that, subject to constraints. Constraints. I feel like that's an important thing to specify. So x and p sub x subject to the constraints that the x coordinate is somewhere along this line, and the p sub x value must be plus or minus the square root of 2m times u. So remember, u, l, and n are to be considered as given, right? You wish to explain this macrostate and count the number of microstates that are consistent with it. Right? And so x has to be here, and p can only be one of these two values, which is interesting, right? If you've given me a total energy, it basically says you've told me the momentum, and it could be going to the left or it could be going to the right, but it's one of those two. So the concept that I'm introducing now is really important. It's one of your takeaways from this course, and it's going to figure prominently in your first midterm exam as well as the final, and that's the concept of phase space. So what I'm drawing in this graph is the phase space of this example monatomic ideal gas. So I take the microscopic variable x and I make it the horizontal axis. And then I take the microscopic variable p sub x and I make it the vertical axis. Okay? So I've constructed an abstract space out of the possible microscopic coordinates that define the microstate of the system. And then inside this coordinates, this phase space, I show geometrically the macroscopic constraints. So along the x-axis, I define a line of length L, and so I just decided to center that on the origin so that it extends from x equals minus L over 2 to x equals plus L over 2. That's not really essential that you do that, but just for simplicity, I decided to. And then there are only these two possibilities for the momentum of the atom, and I indicated those as these two discrete points on the vertical axis at plus 2mu and minus 2mu, right? And so every point that is not the blue color in this graph is a possible value that could be part of a microstate of this gas, right? And so when you view phase space in this way, you reduce counting microstates down to assessing, in some sense, the geometric size of the constrained regions of phase space. All right? So what I'd like us to do is to use phase space geometry as a tool for counting how many microstates there are. So for example, the number of microstates consistent with the constraint L, right? You have to be on this line, is the length of the segment, right? So there's an infinite number of points in here, but somehow the measure of this object is its geometric length, you know, as it would be for any continuous line in Cartesian space. And so let's say that the multiplicity associated with the x coordinate in this system is the integral over this allowed region of phase space, right? And that's just going to be L. So it seems kind of easy, but we're going to rapidly generalize this to real monatomic ideal gases with many, many particles. And it's going to be really helpful to sort of have this perspective of what we're doing in your mind, okay? And so essentially what I'm saying here is we're going to count the total number of microstates by multiplying the number of possibilities associated with the x coordinate times the number of possibilities associated with the momentum coordinate. So we already argued that omega sub x is just the length, right? So that's how, essentially that's a measure of how many x states are available and consistent with the macroscopic constraint of length L, okay? But pretty easy to understand this, I hope. And then the momentum is pretty easy because there are only 2 points. And so you could just say, okay, 1, 2. And so then the multiplicity, omega, I guess I should write, I'll X out of here and write it. The total multiplicity is the product of these two, right? Because for every one point that you choose on X, you could either be here or here. Choose over here, you could be here or here, right? And so for every X possibility, there are the two momentum possibilities. So you multiply. Not surprising. Let me go back and just write this in. I think I meant to write this. Oops. So the total multiplicity is 2L. It's a little bit problematic to write it this way because it looks like the multiplicity has dimensions of length. It's actually length times momentum, because the 2 actually also has dimensions of momentum. But that's something I'm going to sweep under the rug till about 2 lessons from now. So we're just gonna kind of go with this product, even though it is not properly dimensionless yet, and we will fix that at the very end of our calculation. Let's move on to another example, though. That example, I hope, is illustrative, but it is a little bit too simple in that the momentum constraint is so simple. It's just those 2 points. And in any more complicated situation, the momentum constraint is going to be actually the harder one to deal with. So let's change this whole thing to be the same situation except now with 2 atoms. I thought I had 2 atoms inserted here. It's on this one. Sorry, I guess my prep was not quite right for this. Okay, so we've got 2 atoms on the line. And so now our constraints are a little bit different. Each particle is still constrained to be on the length L. We now have 2 particles. And now our total energy is the sum of px squared 1 plus px squared 2. The atoms have the same mass, okay? So now the possible microstates are x1, px1, x2, px2. So we've got 4 coordinates instead of 2. And the constraints are along L, and the sum of px squareds has to be 2mu. So the problem is the phase space now that we would construct by building one axis for each of these is 4-dimensional, okay? And as you know, you can't draw a 4-dimensional space, haha. But what we can do is consider the position and momentum aspects of the phase space separately. In particular, note that this constraint depends only on the p's, this constraint depends only on the x's, and so it's actually possible in ideal gas circumstances to treat x's and p's as separate spaces. Let's do the spatial coordinates first. So we have a 2-dimensional space where the horizontal axis is x1, the position of the 1 particle. Vertical axis is x2, the position of the 2nd particle. And in both cases, the constraint says they have to be somewhere along a line. And so the first particle can be anywhere along this line. The second particle can be anywhere along this line. Important point, multiplicities multiply, right? And all that is saying is, look, if your first particle is here at this particular point, the second particle could be anywhere along here. And if it's here, it could be anywhere along here. And so you need to multiply the multiplicities. And so in this case, you get an L squared instead of L, right? And so I hope it's obvious by looking at this that if you had n particles on this line, the position space multiplicity would be L to the nth power, because you would have n orthogonal axes, n segments on each axis, and you would go multiply, 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 right? And so furthermore, what we'll see in a couple lessons is that in a 3D region with volume Vn, the position space multiplicity will just be the volume raised to the nth power. And it's the exact same analysis as we're doing here. And that's why we're doing it here, where I think it's really obvious what and why we're doing it. And then the extrapolation to higher dimensions and higher number of particles is easy. Or as easy as it can be, right? I mean, when you say easy in a physics class, it means easier than the hardest possible thing you could think of doing. All right, so we're done with the spatial multiplicity in this second example. We have L squared for that. And now let's think about the momentum space geometry, right? The constraint is that the squared momentum values have to sum to this number 2mu, where m is known, u is given as one of our macrostate specifications. So this expression defines a geometry in the momentum part of the four-dimensional phase space. So the momentum part is a two-dimensional phase space, and this sum of squares being equal to a constant defines a circle in the momentum part of the phase space. And the radius of the circle, which I label as r sub p, is just equal to the square root of 2mu, right? So any momentum values on the green circle are consistent with the macrostate constraint of total energy being this expression. And so counting the states on this circle is the same as measuring the circumference of the circle, right? The measure of the number of states on this periphery is just the circumference. And so that's going to be 2 pi r sub p. And so it's 2 pi times the square root of 2mu. Okay? And so let's put this together, right? We've got this system of two atoms on a line. They only have kinetic energy. The total multiplicity is the multiplicity from the two-dimensional x part of the phase space times the two-dimensional multiplicity. I got confused about what I was saying. Real space multiplicity times momentum space multiplicity, right? Both spaces are two-dimensional. And so the basic idea is that this part measures the space available for particle 1 and particle 2 together. And then this measures the total number of momentum states that could conceivably give you this given total energy. And so the final result when you do the multiplication is that the multiplicity in this system is 2 pi L squared for the space part times square root of 2mu. Right? So once again, we've got a multiplicity that has units, and that can't be right. Multiplicity has to be dimensionless. So keep that in the back of your mind, and again, we'll fix this issue later. It's important physics that goes into fixing it, but for right now, we're just trying to develop the tools and the sort of general concept of how do you use phase space geometry to calculate multiplicities for an ideal gas. And so the general definition of phase space is that it's the abstract space constructed from all the spatial coordinates and all the momentum components of all the atoms in a system, right? So for a single particle in one dimension, phase space is a 2D space. Easy to draw, easy to work with. For n particles in 3 dimensions, the phase space will be 6n dimensional, right? Where n is 10 to the 23rd typically. And that is a very unusual space. It's not trivial to work in a 6n dimensional space when n is large. And that's our job for the next couple lessons, is to learn how to do that and what you get from it. So you're just supposed to have in your mind this idea of a 6n dimensional space as having 6n orthogonal coordinates. So it looks something like this, I guess. I'm just kidding. It doesn't look like this. I don't know what it looks like, but you sort of are supposed to have some kind of intuition that there are a bunch of axes, many axes, and you can do geometry when you're given the coordinates, even if you can't see it. It's a nice thing. Yeah, so maybe it looks more like this, a scribble scrabble that I made. You know, I think it's quite interesting to sort of think about sort of the mathematical physics of phase space. So that's an important topic, and maybe I can say a few words about this later. But what we're going to do in the next lesson is develop mathematical tools for working with this kind of garbage, right? Where you can't visualize it, but you have to still do geometry anyway. And we'll sort of set up the full calculation that we'll complete 2 mini lessons from now. So see you next time.